Hello, in this lesson, I wish to go over some, examples to derive and to derive formula rules of differentiability, and I would like you to follow, to do it along my side. And the purpose of doing this is, of course, is twofold. Number one is that you get more familiar with the differentiability rules and also enhance your algebraic abilities, okay, algebraic skills. So please get a piece of paper, pencil, okay, just work along my side and pause and try, you can always try to do your own. And hopefully this will help you. And to understand how we apply the definition of differentiability is very, very important. And this requires some algebraic skills. Okay, so let's start with some simple examples. Okay, for example, suppose we have the first example, right? The first example. And commonly use the function and their derivatives. For example, we have a function, right? F of x equals to 1 over x, right? And we know the domain of this function. The domain, of course, is x cannot be 0, right? So we're doing this on the domain of this function. So when we try to find the derivative, of course, we're going to apply the definition of the derivative. And in this particular case, as you can see, you get to see the definition of function being used, and you also get to do some algebraic, deriving. So this should help you to. So 1 over x plus h, that's f of x plus h. F of x, of course, that's 1 over x divided by h, right? So we have a complex fraction situation. H is approaching 0, 1. Of course, h approaching 0, but not 0, right? So the limit concept, the definition of limit is in our mind. Okay, that's the stage set, that's the situation. So next, we're going to apply some algebraic skill. We're going to apply some algebraic skill. The commonly used algebraic skill in this case, of course, is going to be finding the common denominator. And we use principle number 1. So x times x plus h. That's the common denominator. X times x plus h in the numerator and denominator, so we are multiplying by 1. And the next step, we got, we're doing all of these, in the limit. We cannot apply, of course, you understand, we cannot apply limit law because the numerator approaching 0 as h approaching 0, h approaching 0, so 0 divided by 0. So we're taking limit of something approaching 0 on numerator and denominator, so we cannot apply limit law. So that's why we do these manipulations, just in case, right? Anyone question this? Okay, so we're gonna multiply the numerator with numerator, denominator with denominator. So the denominator will be multiplying the denominator. So this piece is 1, it's gone, right? And then we simplify. When we simplify that, you can see x plus h reduced with 1 over x plus h. 1 over x times x, that's being reduced. And now we got x minus x plus h, the negative sign distributed, so this is minus h. So on the top, we have minus h left. Okay, let's just write one more step. And that h reduces with the h in the denominator. So this h reduced with the h in the denominator. Why we can reduce it? Because principle number one, right? H is not a 0. Now we can do direct substitution because we finally get out of the situation of 0 divided by 0. Okay. Direct substitution will have -1 over x multiply x plus 0. And of course, that's equals to -1 over x squared. This derivative is very commonly used. So now we know the derivative for function 1 over x, right? Its derivative is -1 over x squared. You don't need to make time you don't have to memorize it. If you go through these steps, and of course you can get this formula, you can get this from, the formula we have learned you can get this formula by the derivative, right? X raised to the power n, right? Taking derivative, and that equals to n multiply n x raised to the power n minus 1. But it's just so much easier that you already know it. Okay, commonly used, right? So when you apply the formula, you basically have 1 over x. Take that derivative, and then it's written as x raised to the power of -1, and take a derivative equals to, so n is, you can see that n is -1. N is -1. So here you're going to have -1 multiply x raised to the power of -1 minus 1. So you also get this answer. And this is pretty commonly used. So that's 1 over x squared. And of course, you can also use the other form, which is -1, which is a negative x raised to the power of -2. You can use either one. So this is a very commonly used derivative. Okay. Another example that I think deriving its derivative will be very good exercise for you to practice your algebraic skill is the function of square root of x. Some of you might have, we've done this, but let's do it again, right? And apply the definition of differentiability, right? You will have a square root of function, square root of x. And of course, we know the domain. We do all of these in the domain. The domain is x greater than or equal to 0. And this function and its derivative is very commonly seen. So let's take a look, right? We're going to plug in. And we're getting the square root of x plus h, right? For f x plus h. And the next one is the square root of x, right? And we all know very well how to deal with this kind of situation, which we use a conjugate. We're going to use a conjugate, right? So the conjugate would be the conjugate of the numerator. So right here, so subtraction becomes plus. So same numerator divided by the same denominator, right? The same quantity. So that's multiplying by 1. Principle number 1 is used. And that equals to right? We apply some of these commonly used properties. Denominator multiply denominator. So the denominator multiply h, we need to insert a parentheses. And the numerator, right, multiply the numerator, we're gonna get that a squared minus b squared, you know what I'm talking about. Okay, so I'm gonna put so right here, so we're applying this algebraic identity, right? A minus b times a plus b equals to a squared minus b squared. Okay, and your practice using these, because deriving it really would help you in the long run. Okay, so now we got to this point, and of course we're going to simplify. We keep the denominator as it is in the factor form, and the top is going to be just x plus h here. The bottom, and the subtracting, this is x. So once again, what property are we using here? We're using these two very important and commonly used. Okay, so I'm going to write it down once more. Okay, the square is outside. That's what we are using here. And we know the difference, don't we? Right? And the other one is omega squared inside. And that equals to the absolute value of omega. Okay, we know the difference. We know why the difference. Okay, if you have any questions, please don't hesitate to ask me. Very basic thing, but very commonly used. Okay, so by this time we got some reduction. X minus x, that makes 0. So we have h on top and we have h in the bottom. And right here, okay, h and h reduced. One more step. So this h is reduced with the h on top. So there's a 1 left on the top. And next, we can finally do direct substitution because we can apply limit law. The limit on top exists, the limit on the bottom exists as h approaching 0. And that will be equals to the following. Okay. And you can say, oh, I'm applying limit law, right? You can apply limit law. So h will be replaced by 0. So in the end, we got 1 on the top. In the denominator, we have 2 square root of x. So it's 2 times square root of x. This is also a very commonly used derivative. Okay. And so the derivative of this function, okay, square root of x is 1 over 2 times square root of x. Okay. So very, very commonly used. For other roots, like root 3, root 4, they're less commonly used, but root 3 can be commonly used. Root 3 can be commonly used. I would encourage you to derive for root 3. Okay, for root 3. And the next other commonly used derivative would be like x squared, x raised to the power 3. And these are easily found by using the formula. Okay, so I'm not going to derive it here, but these 2 examples certainly helps with your algebraic skills, algebraic deriving skills. Okay. Other examples, we're going to leave it for some other lessons. Okay. And let's see. Let's prove some properties, differentiability properties. Okay. And one of the differentiability, okay, proof rules of differentiability. Okay, we're going to use the definition to prove the rules of differentiability. We are doing this for, a couple of reasons. One reason is that we're going to apply definition of differentiability. Okay, so we would think of applying the definition of differentiability. That's number one. Number two, improve our algebraic skill. Number three, and I hope that through these process, okay, through your deriving and getting involved in deriving, when we study chain rule, we will have a better understanding of how to apply chain rule. And I think this might help, then at least we can give it a try. Okay. The first one is addition. Okay. And we know that the derivative of two functions, when we take a derivative, is we can take a derivative separately. Okay. Another version would be derivative, right? The two functions, f plus g is equal to derivative with respect to x plus the derivative of the function with respect to x. So you see how I read it? Okay. The derivative of sum is the sum of the derivatives with respect to the same number, the same variable. This is very important for us to understand now, even though there's hardly any concern. Okay, these two notation. The first one, it doesn't indicate by default, so we know it's differentiating with respect to x, right? You see f of x plus h minus f of x divided by h, right? Second form indicates which variable is differentiating with respect to. Okay, and this will become super important when we study chain rule, that we differentiate with respect to which variable, right? So that in that time there will be two layers. So here we want to pay attention to it. So these notation becomes very important for us to understand. Of course, third way of writing it, if you like to make it, we would write the f of x, right? G of x, f of x, g of x. You could write them that way. And the first form pretty much is for memorization, but you have to understand they are differentiating with respect to the same variable. Okay, the same variable. And the last one, they all mean the same thing. Okay, but this latter notation is more specific. Okay, derivative with respect to x. So it's reflected in this case. So this notation can be written as derivative of the function, okay, with respect to x. Okay, so when you differentiate with respect to x plus h. If you differentiate with respect to u is going to be U plus H. Okay, so even though those are placeholders, but they're also indicator. Okay, they're also indicator of which variable we look at the difference of, right? The difference between X plus H and X is H. Okay, all right, without further ado, so let's prove this one and the following one. And we're only going to do the addition, and subtraction is going to be left for you. So subtraction is also true. And then we're going to prove the product rule, quotient rule, which we did in class, but I think I'm going to do it again so that you will practice along my side. Okay, so let's work on the derivative of sum. Okay, and of course, we're going to apply the definition. Apply the definition, and this time is going to be f plus g of f of x. And so this is going to be f plus g of x. Okay. And of course, we understand f plus g of, well, let's start from this one, f plus g of x is equal to f of x plus g of x. And f plus g of x plus h is going to be f of x plus h plus g of x plus h. I know all of these is a whole lot of notation. Okay, so please practice, write it down, make sure you understand these notation. So the next step, of course, we're applying the definition. Step by step. Okay, you can pause and stop and do your own anytime you wish. Okay, so now we're going to substitute. We're going to substitute this piece by its equal. I'm going to substitute that piece, right? That piece by its equal. But this time we need to insert a bracket. Or you distribute the subtraction right there, right? Which is like the next step. If you remove the bracket, all these little details, you would do it, you would see it when you do it, and you pay attention to it. Okay, just watching, I feel it's not enough. The next step is we're going to regroup. Okay, so how do we regroup? Well, we still have that 0 divided by 0 case. We cannot apply limit law, right? So we're going to bring the subtract f of x next to f of x plus a, minus f of x, right? We're going to move it over here, right? So these are regrouped. And we're still on the limit setting. And then we're going to distribute the h to the first difference and the second difference, right? So we're going to have this piece, right? Adding the next piece divided by h. You can see it's a pretty commonly used algebraic skill. But when can we apply limit law? Okay, so let me bring limit law, right? Limit law, where is it? Right here, no, we're not very far. Limit laws, right? Limit law is something we are going to apply, right? Even though we're not in the limit section, but limit law is still, useful, very useful. Now we have two individual limits we want to separate. And now each individual limit exists because we assume that. Right? F is differentiable, G is differentiable. You can see in applying this property, okay, these are called limit laws, we have a fundamental assumption, okay? So the assumption is if F, okay, G are both differentiable, then we have all of these. You can see applying these limit law, actually there's a condition before you apply the limit law, right? Just adding, subtracting. The individual has differentiability. That's why before we apply limit law, we need to check the individual limit exists before we can apply limit law. So here it's the same thing. Okay. So now because of this differentiability is given, right? So since F and G are differentiable, right? Then we can separately finding the limit. Separately finding the limit. So these two limits will be separated as h approaching 0. You can see these steps, as you go through these steps, each step has its reason. And the first limit, of course, to give us the derivative of f of x, right? And the second one is g prime, the derivative of g at x. So now in summary, okay, that is if, right, so this limit law, if f and g are differentiable, then we have just proved the sum of derivative is a derivative. The derivative of sum is the sum of the derivative. Derivative of sum, right? We first have sum and then we take derivative of the sum. It's the same as sum of derivatives. So to separate these two is a conditional. That condition is that both functions must be differentiable at that specific point with respect to the same variable, And subtraction can be done similarly. Just be careful when you're doing that. There's some, negative sign you have to take care of with care, and I'm sure you can do it. The next one we want to prove is that if f and g are differentiable, okay, the product rule, right? If both f and g are differentiable, how about the product? F times g derivative. What would that be? Right? One thing is certain. Okay, one thing is certain. It is not what it is not. Well, the derivative of product is not the product of a derivative. This is false. Even though it is a very common mistake. It's a very common mistake. And what is it? Okay, so if you see the proof, then you realize, yes, it cannot be. It cannot be, right? You will not make that mistake, hopefully. All right, so it is f times g prime plus f prime times g. You can write it in any order, any which way order you like. And there are also these different versions of it. Okay, all these similar to, addition, subtraction. There's a multiplication, and in the multiplication case, there are also these different versions, right? We want to specify the derivative it is with respect to, right? F times g, right? It would be f times derivative of g plus g multiply derivative of f. You can see the order is slightly altered. Okay, the order here is slightly ordered because I put a g in front of it. It's because we want to avoid that confusion. Okay, and of course, the third version of it, all of these points, they mean the same thing. Okay, so this is f of x, e of x, e of x, f of x. So we point this out. It's to illustrate that they're with respect to the same variable. Okay. The derivative is with respect to the same variable, x. Okay, with respect to the same variable, i.e., we're applying the definition as what we have on the top. And this time, let's see how we prove it. Okay, no, this is a false, right? So let's prove it. Right? When we prove the derivative, and this time is f times g parentheses derivative. So now it's f times g. So this is changed to f times g, f times g. X plus h, that's the indicator of the derivative. Okay. See here, we emphasize with respect to x, Okay, so let's get started. Well, f times g is f of x times g of x. Okay, and of course, f multiply g would be f of x plus h multiply g of x plus h. The dot I have there is optional. I can put it there and I can remove it. It doesn't really make any difference. All right. Next, we're going to apply the definition. So we're going to look at this limit. Okay, I'm going to bring the whole thing along. Okay. And plugging in, right? We're going to do a bunch of substitution. Just be very careful. F times g of x plus h. So that piece is replaced. Oops. Oh. So that piece replaces that whole piece. F times g of x is replaced by that form. Okay. And of course, we cannot apply limit law because numerator approaching 0, denominator approaching 0, the same reason. So we have to separate them somehow. So how do we separate them? Right? So what technique do we use? Well, we're going to use adding 0. Principle number 2, adding 0. And so how do we separate them? Well, we're going to add something and subtract something. Okay, so certainly we're going to add a 0. But this 0 is carefully chosen. So we're going to get f of x times g of x plus h. We're going to add this piece and we're going to subtract the same piece. So we're adding a 0. Okay, so we're adding a whole piece. That is a 0. Okay, and now let's see what we can do. Now let's see what we can do. All right, we are going to group. Okay, we're going to group the first two, and we're going to group, well, actually, if we do subtraction here, we're going to do addition here. This will be much easier, okay? Subtraction, adding here. So this way we don't have to move terms around, okay? But it's a 0 anyway, so subtract 1 and we add 1, okay? Is that clear, everybody? So I just switch the order. Now, the first two terms are naturally, this way we just naturally combine them. Second one are also naturally combined, so we're separating them. And after we separate them, so the next step, okay, the next step, we're going to write this way, okay, the limit. We're going to separate the numerator into two separate ones. Hold on. Okay, I just want to leave a little space. And so we're going to have something like this. Okay, h is a common denominator. And these two will go with the, okay, I better save the file so I don't make a mistake. Let's see. Differentiability. If rules. Okay, so that way, so I'm going to take the first two and put it here. And I take the second two and put them here. They're separated. And all of them are in the bracket. They're still, limit. They're not separated because we cannot separate it by limit law until we have the proper setting. Okay. We still cannot separate the limit. Okay. But now if we do some, manipulation here, right? We can identify those individual limits that exist, right? So the first one, we have f of x plus h times g x plus h. G of x plus h and g x plus h, these are common factors. So we factor them. We're going to put them separately. I put a bracket here. And g of x plus h, I'm going to put it on the side. Okay, g of x plus h is a common factor. And for the next one, we're going to do the same thing. We factored out the f of x, right? We're going to put it on the side. Now they're separated. Now we look at this. There are 4 individual limits to look at. Okay, we have 4 individual limits to look at. This one has an individual limit when h approaching 0. That's the first one. second one is g of x plus h, right? This one is taken limit as h approaching 0. And the third one and the fourth one. And we declare that each one of these limits exists. Each one of these limits exists. Actually, I can remove this bracket. I can remove this bracket. Okay. So now we have 4 individual limits. They all exist. How do we know? Because f is differentiable, g is differentiable. So these two, the differentiability covers that limit exists and that limit exists. F of x, there's no h there, right? So it's treated as a constant. So this one, as h approaching 0 has a limit, we get to apply limit law for the constant. It will be treated like constant. How about g of x plus h? Well, if a function is differentiable, it is continuous. So here we're going to put some narrative here. Okay. Since both f and g are differentiable, right? That's given. Since both f and g are differentiable, then the individual limit, this limit exists, right? So this limit exists. And that limit exists. They both exist. And differentiable function is also continuous. Okay. Differentiable function is continuous. That means that when h is approaching 0, right? So as h approaching 0, this limit exists. And that is equals to g of x. Right, so we get to use the theorem, and that theorem is differentiable function is continuous. Right, so this is on your flashcard. So all 4 individual limits exist. So now we can go back here, right? We can go back here and apply these individual limits. And of course, by this time, we can just remove these, right? So this time we can apply these individual limits. So let me show you how we apply that step. That step shows that the limit can be taken individually because each individual limit exists. So we are applying limit law. Okay, so as you can see, before we apply limit law, we check each individual limit exists. And that's a must. That's a must. Now it's just a matter of plugging in, right? This limit is, we can write it down here, right? F prime of x, right? And that's g prime of x, right? And also applying differentiable function is continuous, so we apply that too. So that replaces that limit. Multiply, this piece is replaced by g, right? Replaced by g. Adding, this is treated as a constant. So f of x multiply g prime of x. So that's how the product rule is approved, Okay, so in the end, we got this product rule. We got this product rule. We got this product rule. Okay. If you know the proof, I think it's less likely you're going to make the mistake like this. Okay, I hope. Okay, so please do go through these proofs. Okay, and product rule certainly doesn't look that intuitive, but if you look at the proof, I don't think you will ever make that mistake, which we saw commonly. Okay, so that's the product rule. Quotient rule. Okay, so next let's prove this quotient rule. Quotient rule, what does that mean, right? So we've done adding, subtracting, multiplying, dividing, and the assumption is the same. Okay, both individual functions are quotient rule. Quotient rule. You can see if you go through these process, I think it should be very helpful when you do it by hands, as how to apply those rules. What it means is that if we differentiate two differentiable functions in quotient form, what would that be? One thing is certain. It is not what it is not. Okay, this is another common mistake, is that f prime divided by g prime. So don't ever do this, okay? This is a terrible mistake. Okay, it's not this one. Okay, so this is a terrible mistake. Okay, mistake. So what is it? Right, what is it? And of course, some of you know the formula, some of you don't. Well, it is actually not very intuitive. Okay, it's g squared on the top, and there's a difference. Okay, but the difference has to be in the right order. So f prime times g minus, okay, f prime times g, and then f times g prime. You can see it is not intuitive at all. Quotient rule, right? Both functions involved are differentiable. And of course, there are other versions of it. The other version, of course, is only look like this. It looks more complicated, but it has its advantage. Okay. F of x divided by g of x. The more complicated version is the following. Even though it looks complicated, but it's clearer. Okay, it's clearer. So this latter version, okay, f divided by g, both are differentiable. G of x is being squared. Okay, and on top, we're going to take derivative of f, which is on top, right? F of x, and then multiply g, put the g of x in the front. Why do we do that? It's to avoid confusion. It's to avoid confusion, because if we put g behind, it could be confused. It could be confusing. Okay, subtracting. Okay, and this time f of x multiply derivative d of x. G, this time we differentiate g. Okay, so that's the quotient rule. Common mistake. Okay, so let's prove it. Let's prove it. To prove this one, of course, we're going to apply definition once again, right? What is the definition? The definition that we always been using, but this time f is replaced by f of x divided by g of x. So now this part, right, is replaced by f divided by g. So the rule, so now this function is going to be, this is divided by g, right? Divided by g. You can see how that definition is applied to it. And x plus h, f of x. So we are differentiating with respect to x. Okay, with respect to x. You're going to hear me saying with respect to which variable a lot, because I need to say that to clarify. Okay, especially under chain rule. It's very important. Okay, and we will learn chain rule very soon. Okay, on Tuesday. All right, or next week, next time we see you. All right, so what is f divided by g of x? Okay, notation. We have f of x divided by g of x. That's what it means. Okay, how about the latter one? The latter one is defined as f of x plus h divided by g of x plus h. Oops. Now we're ready to plug in. Now we're ready to plug in. Okay, the latter piece replaces is equal, and this piece replaces this part. You can see this will really, if you do this, it really enhance your algebraic skill. Okay. All right, complex fractions. How do we handle complex fractions? We already know it, right? So what we do is that we're going to find the common denominator. And what is that common denominator? G of x plus h multiply g of x. So g of x plus h multiply g of x. And then we create a number one, principle number one. Anything times one stay the same. Why do we have to do this, by the way? Well, because we have a 0 divided by 0 case, limit law does not apply. And we're going to have to manipulate it algebraically to create some individual limits that exist so that we can separate. Right, so right here, we're doing this algebraically because we cannot apply limit law directly. And next, of course, denominator times denominator, numerator times numerator, right? So we're going to multiply, right? This is removed, and we're going to reduce it. Okay, you can see this step and do it on the scratch paper, but I'm just going to do it this way. G of x plus h, g of x plus h, that's reduced, right? G of x, take away g of x. So that part is also reduced. So we ended up with a simpler, complex fractions being taken care of. But we still cannot separate them, right? Because we don't know if we don't know if the limit on top is going to be approaching 0. The limit on bottom is going to approaching 0. 0 divided by 0 as h approaching 0, we cannot apply limit law. So we have to continue. And what do we do? What do we do? Once again, adding 0, adding 0. So what are we going to add, subtract? We're going to subtract, add, or add, subtract the same number, applying principle number 2, right? Anything add 0 stay the same. So we're going to add f of x multiply g of x. And we're going to add the same thing. Subtract the numbers and add the same numbers. We're adding a 0. And now we want to see if we can separate them, right? And we are going to separate them. So we take this denominator, okay? And we're going to separate that into 2 terms. So this piece, so this is going to be adding. Okay, we don't need that adding. The denominator is common. Being shared by these 2 separated, and they're still under the same bracket. We cannot separate them yet. And then what do we do? And then what do we do? We're going to factor something out. We're going to factor something out, right? So what can be factored out? What can be factored out? Well, on this piece, we have g of x, right? We're gonna factor out the g of x, and we're gonna factor out the g of x, and we're gonna put it right here. You might notice that we can cross out the g, but don't do it. Don't do it yet. Okay. On this piece, f of x is factored out. Okay, so we're going to factor out the f, and we put it in the front. Because now we're creating some individual limits that exist. So we're going to do some more algebraic manipulation. Okay. And you can practice, on your own as to how to separate them. Okay, so one thing is that I'm going to bring these 2, right? And put it under g of x. And that individual limit exists. And now I'm going to bring these over under f. And that individual limit also exists. This individual limit exists. Can I reduce anything like that? We cannot reduce it. So let's see how many individual limit we have. This is an individual limit, and that's individual limit. They both exist. F of x, g of x are treated as a constant. The only thing that g of x plus h, that limit exists because differentiable function also is continuous. We're going to bring back that differentiable function is continuous. That's the same reason, right? That's the same reason, right? And what else? Same reason, right? Since the 2 functions are differentiable, so we use the same arguments. So all these arguments just demonstrate that individual limit exists. We can take them. We can take these individual limits. How many do we have? 1, 2, 3, 4. So now we can separate. Okay, so I'm going to copy this down. Okay, I do this for clarity. And remove all of these because this work has been done. So now we can separate the limits, applying limit law. You can see applying limit law properly. That's all we are doing here. Okay, so we're going to bring this here. and the limit is separated individually. So now we are applying limit law after we checked each individual limit exists. Okay, and the rest is just a simple substitution. Over here, and of course, that's f prime, right? So that replaces that limit. Multiply this piece. What is this piece? Well, that piece is g of x divided by g of x squared. We didn't reduce it because we will otherwise have to bring them back. You could, I mean, plus, oh wait. I think we made a mistake somewhere. It should be a subtraction. Let's go back to see what have we missed. Yes, here, you see, I made a mistake somewhere. So this is subtracting g of x minus h, right? But now, actually everything we've done here is correct, except now if I switch these two, because if I switch these two, okay, if I switch these two, I will bring out a negative sign. Okay, so this is a negative, and this is g of x minus g of x. It doesn't affect the limit though. So we should have a minus sign right there because we switched, so this is subtraction. Okay, I didn't make a mistake, it's just we didn't switch. Now we switched. And the individual limit exists. You know, we could have done it there. We could have done it here because that would make it, just look better. Okay, no mistake is made, now subtraction. So now we know how we get the subtraction because we switch these two. All right, okay. Subtracting, okay, and that piece, we use a continuity, and that will be equals to f of x divided by g of x squared. See, that common denominator is right there. Okay, we use a continuity and then g prime. Okay, one more step. We have the same denominator, right, which is g of x squared and f prime of g, right, f prime of g multiply g of x minus f of x multiply g prime. So that's the quotient rule. Okay, so if you've done the proof, right, you don't have to, I'm not going to test you the proof, but if you've done the proof, you've seen the proof, then you will not make this mistake. Please don't make me this mistake. Okay, so now let's look at the quotient rule. It's been proved. The quotient rule is being proved. Here we go. The quotient rule. Okay, two different versions. F prime g, subtracting f times c prime, c squared in the denominator. And I hope this proves that if you go through it yourself, okay, do it at like once or twice, then you will be totally familiar with these rules and you won't make those mistakes. And the other thing is that I wish you guys to be familiar with differentiating with respect to what. Okay, with respect to X. In the future, when we talk about chain rule, will be with respect to you, right? So be familiar with that situation. So when you understand the chain rule at that level, which we're going to talk about next time, it will be, I hope, eradicate a lot of the common mistakes we've seen. Okay, thank you for watching. Until next time.